invitation and the opportunity to be here. Today I'm going to share with you some of the research I've been doing on dielectric spectroscopy of modulated liquid crystal. I will start with some backgrounds, then I will talk about the motivation of this presentation. And I will show you a practical problem, which is the dielectric spectroscopy on a Ka material, which shows the new nematic order, the twist band phase. This is a experimental research in collaboration with the Kent State University from the Dr. Yakli's lab. And I will show some conclusions and then future perspectives. So first, some of the backgrounds here. Let us start with the empty cell. So if you see a capacitor, the permittivity here is the permittivity of the vacuum. And because the plates have opposite charge, there is an electric field inside. But if you insert a dielectric material between these two capacitors, the permittivity has been changed to the permittivity of the dielectric material inside. And because of the electric field, the dielectric material will polarize in response to this field. And this is the way dielectric material is supposed to behave in a constant electric field, for example. So the permittivity will express the ability of this material to polarize in response to the field. So now imagine an alternating field applied to the cell. You see an effect on the behavior of each polarization mechanism. If you apply an electric field which is varying with the frequency, you see different polarization mechanisms in the system. For example, if you apply an electric field up, the direction of the polarization will follow the field. And you also see a dielectric constant that depends on the frequency. When the electric field is pointing down, for example, the direction of the polarization will follow the field in order to switch, in order to switch to align with this field. But this cannot occur instantaneously, immediately. There is a relaxation time in the system. This means that if you increase the frequency of the applied electric field, you see a decay in the dielectric constant as a function of the frequency. If you go until the relaxation frequency of the orientational mechanism, for example, you see that this orientational mechanism is inactivated, and there is a decay in the dielectric constant as a function of the frequency, here represented by the dot red point in the graph. So I study how polarization mechanisms, the modes, depend on the frequency of the applied field in liquid crystals. We have heard about liquid crystal here, but liquid crystals are a state of matter between a solid and a liquid. It can show, for example, birefringence, but also is capable of flowing. The most studied mesophase is the nematic phase, for example. It is usually formed by rod-shaped molecules, and these molecules are not arranged in the layers, but they tend to point the same direction along a director. And when you apply an alternated field in the nematic phase, you will see basically two polarization mechanisms in the system. First, the reorientation around the short axis, which we usually call the flip-flop motion. Second, the reorientation around the long axis. But the motivation here is that the principal material that I'm going to talk about today is a material that have flexible arms and a band shape. So the material is called here Ka 0.2, but it's a mixture of flexible band core dimers. And it shows an nematic phase, but also the nematic twist band phase. The experimental research here was a collaboration with the Kent State University, and the measurements on this material was made in the laboratory of Dr. Iacli at Kent State University. And we studied the Ka material here, but especially the nematic twist band phase from the experimental point of view. We did dielectric measurements, spectroscopy measurements on this material, but also TEM, first fraction TM, to study how this material behaves under an electric field, for example. But first, let me tell you about the NTB phase. So, the nematic twist band phase was predicted years ago, but only recently it has been observed experimentally. Usually, the molecules that form this phase, twist band phase, have band shape and a very small band elastic constant. So the molecules there, they tend to twist and bend at the same time, in such a way that the director follows an oblique helicoidal structure, which is in a nanoscale range. The twist band phase has been studied by several groups, research groups, but here are some of the groups research on this nanoscale structure from different groups. Here's an example of another material that shows the twist band phase, the CB7CB. This is a beautiful picture from another group. They show the nanoscale structure of the helicoidal. You can see the pitch in the nanoscale range. But here I'm going to talk about dielectric spectroscopy measurements. So my contribution in this work was the dielectric measurements on this phase. And we wanted to study how this material behaves under an alternated field to investigate the polarization mechanisms of these molecules. Once there is a variation of the polarization, we can say there is a variation of the dielectric permittivity as a function of frequency. And there is a real part and imaginary part. So to understand how this works, I'm going to talk about some formalism here. So usually the dispersions in this material is studied by the Debye type model, for example, or the CoCo model. And we use this equation to fit our data. So I'm going to just explain how this equation behaves. Here's an example. So the blue curve is the real part and the red curve is the imaginary part. You see each relaxation frequency corresponds to a decay in the blue part, the blue curve, and a maximum in the red curve. But in dielectric spectroscopy measurements, we usually insert the liquid crystal between the cell, and this cell usually has a geometry similar to a capacitor. Then we measure the impedance of this cell. But decaying materials, like the crystals, show dielectric anisotropy. So we had to align the material with a magnetic field in order to obtain the parallel and the perpendicular component of the dielectric permittivity. So here's an example, letter A, of the molecular arrangement in the nematic twist band phase. And letter B and C are the parallel and the perpendicular component. So we did the measurement on first. Here we have the frequency dependence of the parallel part. This is the imaginary component of the dielectric permittivity. So we selected some temperatures. You can see the nematic phase and the nematic twist band phase. Let's see the nematic phase first. You can see high frequency mode, which strongly depends on the temperature, but also lower frequency mode in the nematic phase. And if you go to the nematic twist band phase, you can see two dispersions, one the high frequency mode and another one at one order of magnitude below, lower frequency. So this is the frequency dependence of the perpendicular part of this imaginary component. In the nematic phase, we observe only one relaxation at a high frequency. But in the nematic twist band phase, we could see two relaxation modes here around megahertz and then lower frequency. But the main purpose here was to obtain or extract the relaxation frequency. So we fit the data with the formalism in the dielectric research here. So we have dependence on the frequency relaxation, and alpha tells us if there is one relaxation or a distribution of relaxations. And we did it to obtain the fitting. We could obtain the relaxation frequencies as a function of the temperature. So here we can see three modes in the nematic phase and two modes in the nematic twist band phase. Each mode has an activation energy. So let us see the black curve first. So the highest mode shows the lowest activation energy. We assign this mode to the flip-flop, to the bending and flexing of the flexible arms. And you can see when you go to the nematic twist band phase, there is an increase of the activation energy. We believe that this increase in the energy is because of the nanoscale structure. It's hard for the dimers to maintain the motion in such a structure, bend and flexing structure. But if you go to the red curve, which is the medium frequency relaxation, you observe a flip-flop motion. This is in the range of the flip-flop motion. And it also increases the energy when it goes to the nematic twist band phase, as you can see right above the red curve. The interesting thing here is that these two modes, the highest one and the medium one, can be seen in the nematic twist band phase in both components, parallel and perpendicular components. We expected this because we can see a bending and the flexing in this phase. So we could see this relaxation in both parallel and perpendicular components, for example. And the lowest relaxation mode here, the pink curve, has the highest activation energy. So we believe that this is a cluster flip-flop, and it also has been observed in rigid band core materials. We also observed that there is a low frequency relaxation mode in the nematic twist band phase. Here you can see better. This is the real part of the dielectric permittivity as a function of the frequency. We selected the 65 degree, which is in the nematic phase, and the 34 degree, which is in the nematic twist band phase. We wanted to study the NTB phase at lower frequency. This is something that we are working on to see how this material behave at much lower frequency. About the conclusions, so we have seen that the dielectric constant can tell us how many polarization mechanisms a material possess. And the dielectric measurements here on the Ka material reveals 3 types of dispersion, nearly the bi-type dispersions process in the nematic and nematic twist band phase. So we could see also that dielectric measurement can tell us a little bit more about this NTB phase and how the nanoscale structure can affect the dielectric property of this material. For future perspectives, from the experimental point of view, we have studied the Ka material with the chiral dopant added to it, and we observed that it induced spontaneous modulation in the chiral nematic phase. And when we added the chiral dopant, we saw stripes, textures, but we found out that these textures, these stripes are not due to the nematic twist band phase. These are due to the instabilities of because of the chiral dopant. So the material prefers to bend instead of twist because of the very low band elastic constant. I would like to thank the IIP for the financial support and my university, UTFPR, also for the opportunity to be here. I would like to thank the group of Kent State University for the research present here, and the Maringá State University for the collaboration. And I would like to very much thank you for your attention.